welcome to today's webinar event on properly sizing your positive displacement pump. Today we will focus on just our positive displacement pump line, so that'll be our universal series, and we'll have a little bit on our twin screw pumps as well. However, before we get started, I'd like to introduce myself. My name's Tanner Dahlhauser, and I truly do want to thank you all for joining today as we discuss how to properly size your positive displacement pump. I am SPX Flow and Waukesha Cherry-Burrell's EPC and Engineering Specialist, and I will be your technical host for today's webinar. I help customers and engineers with both training on our products, as well as project design and quoting of our products for these engineering and EPC customers. I've been with SPX Flow since 2021 in a number of different roles, and I'm really happy to be here and really glad that you've joined us today. It's my goal to help you guys understand conceptually how a positive displacement pump operates and how to properly size and configure the correct pump for your application and the manufacturing conditions of your projects. A few housekeeping notes before we get started. As an audience member, you will not have audio or video capability, so please use the Q&A feature to submit any questions throughout the presentation, and I will answer as many as I am able to at the end of our presentation today. If we don't have time to answer them all, my contact information is on the slide here, as well as at the end during the Q&A session of this session. So let's get started with the discussion on properly sizing your positive displacement pumps. At SPX Flow, our purpose is to improve the world through innovative and sustainable solutions. As far as it relates to sizing pumps, an innovative solution is going to maximize your efficiency and uptime. By maximizing your efficiency, you'll have a more sustainable solution with lower operating costs and less downtime in the field. Today, we will discuss some guiding data, such as apparent versus static viscosity, as well as our inlet pressure conditions and positive displacement pump portfolio. We'll then jump into some rotor and seal selections on the configuration side, and then do some actual sizing with paper curves and electronic sizing programs. We'll round out today's presentation with application examples, including some general guidance as well as some specific examples on how some minor details can have large implications on your sizing. And that's my key takeaway for today. It's something I do at the beginning of every presentation, something for you all to keep in the back of your minds as we go through today's presentation on how minor configuration or sizing details can have large implications on our pump selections. Jumping into viscosity and net inlet pressures, I first would like to start on viscosity. On the screen here, you'll see a viscosity plot from our applications lab viscosity testing. It maps the viscosity as the shear rate is increased throughout the testing. Now, there's two key points here that I want to bring forward. The first is that we size things based on both the static and apparent or pumping viscosity of the pump. And two, not every product is going to have a curve that looks like this. What we see here is a thixotropic or shear thinning fluid. What that means is as we increase the shear, the viscosity goes down. And the example for that I always give is ketchup in a cup, on your table is pretty thick, but as you squeeze it out of the bottle or put it under shear, that viscosity is much thinner and it flows much more smoothly. So what we use the viscosities for as it pertains to sizing pumps, we look at the static viscosity, which is going to be at a shear rate of 1, so the very left end of the plot here, and we'll use that to size the horsepower of your pump. We want to make sure that we have enough horsepower available that if you have a line down scenario, that Waukesha pump will be able to start right up and get your process moving forward again. However, we want to size the speed that the pump operates at its apparent or pumping viscosity. And we calculate that by looking at the shear rate in the line sizes. So to do that, we'll need both the flow rate and the line size. We'll calculate the shear rate for you and kind of understand where that viscosity lives. For example, if the viscosity is, say, 10 at 110 degrees, we can see that that's about 4,000 centipoise. If you don't have a viscosity plot like this, our applications lab can run these tests for you. Get in touch with your channel partners if you want to learn more about that. We also have thousands of these in our database. So as long as you know what your fluid is, we can generally get a pretty close approximation for you. The other guiding data that I wanted to cover today is net inlet pressures. And what this really is pertaining to is cavitation, which is by far the largest amount of damage that I see on our pumps. Almost every plant I've been to has at least one pump that has some minor cavitation in it. And cavitation occurs when the net inlet pressure available is less than the inlet pressure required. What that essentially means is the pump is requiring a certain amount of suction pressure to properly feed the pump, and we're just not supplying it enough pressure, which causes cavitation. The net inlet pressure required by the pump is something we provide to you on our quotes as kind of a calculation that we do in-house. And what we want to make sure is that our net inlet pressure available in your system is greater than what's required in the pump. In the jade green on the left side, you can see the equation for calculating net inlet pressure available. Otherwise, our channel partners or our applications team can do that calculation for you as well if you can give us the suction side conditions. If you're having cavitation issues, or we've given you a net inlet pressure required and it is less than what is available, or greater than what is available, I'm sorry, a couple things that we can do is increase the line size on the suction side. For example, if you have a 2-inch pump inlet, we would recommend using 3-inch suction tubing and an eccentric pipe reducer at the inlet of the pump to bring that down to 2 inches. A larger line size is just easier to feed into a pump. We also like to see 7 to 10 diameters of straight tubing leading into that pump. Using our 2-inch pump inlet example, that'd be anywhere from 14 to 20 inches of straight piping. And essentially, that just ensures that we have laminar flow as we come into the pump, but there's no turbulence that may introduce some cavitation or things like that. So a little bit of straight piping definitely helps. What we don't like to see is a 90-degree inlet or elbow right at the inlet of the pump. So please try and avoid that if you can. Now, getting into sizing a little bit more, it's important that we not only size and configure our pump correctly, but we're also selecting the right pump from our pump family or our pump portfolio to properly meet your application needs. So the Universal 1, that's a sanitary pump, meets all of our 3A requirements. However, it is clean out of place only. And that's very important. Otherwise, you'll have some bacteria buildup in that pump if you're using it to clean in place. The things that are really great about the Universal 1, very, very easy to work on. There's no torque specs required on the pump, so it's very easy to just whack it tight and let it go, and you're ready to operate that pump again. You really only need about 3 or 4 tools too, which is really nice. Now, it is only available in O-ring and mechanical seals. However, those pressures that we have in that pump, because there are no torque specs, are much lower than what we see in the Universal 2 and 3 pump families. Moving over to the Universal 2, that is also a sanitary pump. However, it now can be cleaned in place. We've introduced torque specs onto this pump, so it's a little bit harder to work on in the sense that you need a torque wrench to make sure everything is tightened down correctly, but that ensures a cleaner pump, and it also allows us to get to higher pressures. With the Universal 2 and 3 series, we can get up to about 500 PSI in certain pump models, whereas the Universal 1 is limited to around 200 PSI. The Universal 2 ND is a industrial version or a non-3A version of our Universal 2 pump. It also has torque specs required, and really, by removing some of those sanitary features, we're able to bring the price point down on the Universal 2 ND to make it a little bit more competitive in that industrial market. The Universal 2 ND is available in mechanical seals, so single and double, as well as lip seals, well, triple lip seals, namely being the #1 option there. The Universal 3, again, another sanitary pump, able to be cleaned in place, has the same kind of torque specs as the Universal 2. The key difference here, we have front-loaded seals in the Universal 3. So when you need to do a seal replacement on the Universal 3, you pop the cover off, take the rotors out, and you can do your seal replacement without ever taking the pump body off. Contrastly with the Universal 2, you have to take that pump body off in order to get to the seals, which are in the back of the pump body. So a couple different things for you guys to consider as you look at your applications and what pump actually best fits your needs. I want to take a quick tangent here to talk a little bit about the twin screw pump. Most of this presentation is going to focus on sizing these positive displacement pumps on screen, but I would be remiss if I didn't touch on our twin screw offering as well today. The Waukesha twin screw pump is our twin screw offering at the moment. The one question that I always get when it comes to sizing and selecting twin screw pumps is what screw pitch do I select? And generally my guidance there is that the larger the screw pitch, the more displacement per revolution, and a little bit less efficiency as you increase that screw pitch. That's twofold. As we make the screw pitch larger, there are less contact points in the pump body itself. So you may see some marginal efficiency losses at lower viscosities. However, because it's a larger pitch, every time that screw rotates, we're going to see a little bit more displacement per volume. So when I'm meeting those really high flow rates, I want a larger screw pitch diameter. And if it's a lower flow rate, lower viscosity, I'm generally selecting the smaller screw pitch diameter. Now, twin screws in nature are really great pumps for their applications. They're great in low net inlet pressure situations. They can be self-priming by design. And then there's that classic tried and true, it's a 2-in-1 pump. You can pump your product at low speeds and speed that pump up to run your CIP and get rid of the traditional PD pump centrifugal pump combo. However, there are a couple caveats that I wanted to bring up in the next couple slides here, just to say that the twin screw pump may be a great pump for the application. There may be a better pump for the application, whether that's the universal series or a centrifugal pump. So it's important that we evaluate all of our options. And I wanted to highlight a few key features here to be aware of with the twin screw pumps. Because they're built with much larger clearances compared to our universal series, twin screw pumps just by nature are not going to be as efficient. If you look down below, we have a sizing example here of 50 gallons per minute at 100 psi of pressure at about 1,000 centipoise product. With our universal 2, it's 100% efficient. You can see it's got about the same inlet pressure requirements, a little bit lower horsepower requirements, and we're running that pump much slower. Compare that to the Waukesha twin screw in the same application, only about 83% efficiency there. So it's really important that we consider efficiency when it comes to sizing our pumps. The other example that I think is a little bit more glaring and of concern is the motor horsepower requirements. This is a sizing that I did for this webinar. I rounded some numbers to make it look a little bit better, but these are right in the ballpark of the actual sizing that I did. Twin screw pumps can result in massive and very expensive motors if we're not careful. When we're running a high viscosity product at low speeds and that CIP duty at higher speeds, what results is we can get a very large pump to accommodate the CIP speeds with large rotor pitches that slows our product down even more. So in the sizing that we've done here, the product is 10 horsepower at 300 RPM, and the CIP sizing is 20 horsepower at 1200 RPM. The result of this sizing is a 40 horsepower motor. And the reason for that being is as we change the motor speed down from its rated speed, we proportionally lose horsepower. So if we have 40 horsepower at 1200 RPM and we cut that speed in half, we're running it at 600 RPM, we only have 20 horsepower available for that motor to operate on. If we cut that in half again, we're down to 300 RPM, and we're down to that 10 horsepower available. So those high horsepower requirements on the product can often result in very, very large motors that can almost be as expensive as some of the pumps, depending on the application. So please just be cautious. This isn't me saying that twin screws are not right for any application. They are a great pump in our portfolio. There are just some applications that we prefer our universal series, that we may prefer a centrifugal pump. It's all about selecting the right pump for the right application. Now, jumping back to our universal series, our positive displacement pumps, let's get into some rotor selection. Rotor selection is really a balance between two key features: maximum efficiency and maximum runtime, or making sure that that pump runs for as long as humanly possible. When we're talking about the clearances in our rotors, that balance between efficiency and longevity, there are three key tolerances or clearances that we're concerned with. The first being the back face clearance, denoted by the letter A on our screen here. That's the distance between the back face of the rotor and the pump back face, or the front face of the pump body. We also have our rotor to body clearance, denoted by letter B. That's going to be our outside diameter clearance between the rotating piece of the rotor and the pump body itself. And lastly, we have the front face clearance. That's going to be the distance between the front face of the rotor and the cover. So it's important that we look at all three of these different clearances and make sure that we're considering how can we be as efficient as possible without making any contact inside of the pump body. Now, contact is unavoidable, but because our rotors are made from alloy 88, which is a non-galling alloy that we cast right up here in Delavan, Wisconsin in our factory, it is non-galling. So if you happen to make that contact, you will damage the pump, yes, but that pump will still run and give you performance and efficiency even though there's some damage in it. It won't destroy the pump, it won't take your line down for too long, and you'll be able to get back up and running while you wait for those spare parts. So jumping into our rotors here, the first thing that I want to mention is there is a slight naming difference between the Universal 1 and 2 rotors and the Universal 3 rotors. What we had found during testing is that most of our applications are such high viscosities that what was called the hot clearance rotor was still 100% volumetrically efficient. I mean, we're talking about very small clearances here, everyone. Our back face clearances could be as low as 0.02 of an inch. So these clearances, although we're increasing them because of our non-galling alloy and the way we've designed our pump, those hot clearance rotors were still 100% efficient with a lot of our products that we were pumping and selling our pumps into. So when we released the Universal 3, we decided to rename the hot clearance rotors to our standard clearance rotors. And then what was traditionally standard is now our low viscosity rotors. So just a slight naming change there. The pump performance is still going to be the same regardless of the rotor. If it's a standard U1 or a low viscosity U3, you'll still get the same exceptional performance. For the rest of this slide, I'm just going to use the Universal 1 and 2 names as to not confuse anybody too much more than I already have. So the reason that we would select our hot clearance rotors is when that temperature gets over 180 degrees Fahrenheit. We use our hot clearance rotors for temperatures anywhere from 180 to 300 degrees Fahrenheit. And generally the clearances that we're changing there are going to be the rotor to body clearance on the outside and that front face clearance to allow for some thermal expansion of the product or that hot product will cause on our rotors, just to make sure there's no thermal contact there. We'll also use our extra hot clearance rotors for any applications above 300 degrees Fahrenheit. There we're going to be increasing all of our clearances to allow for that additional thermal expansion from the additional product temperature as well. Now, there's some viscosities listed there as well. The general guidance that we use is anything above 200 to 300 centipoise is going to be 100% efficient with our hot clearance rotors. So that's just the general guidance there. If it's below that temperature or below that viscosity, we're going to want to lower the clearances down and use a standard or low viscosity clearance rotor. Some less common rotors that we have used in the past, and I think they're really great to know about depending on your application. The first one being front face clearance rotors. These are for fairly hot products that are low viscosity. So low viscosity products between 180 and 220 degrees. We use standard clearance rotor clearances on the back face, standard clearance on the rotor to body, and then hot clearance on the front face. The reason for that being is we want to make sure this is as efficient of a rotor as possible because of the low viscosities. However, we want to account for the thermal expansion of this moderately warm product. So we increase the front face clearance because the first thing that expands in the pump is the shaft. It's going to push that rotor towards the cover slightly. So we add some additional clearance there to ensure that there's no thermal contact. The next one is our stainless steel rotors. So alloy 88 has similar corrosion resistance to the 300 stainless steel families. However, if it's not chemically compatible with your product, we would use the stainless steel rotors. The standard rotor clearance on the stainless steel rotors is the same as our alloy 88 extra hot rotors because we cannot have any contact because we're scared of getting any galling in that pump. So some additional clearances. However, if we account for it right out of the gate, it'll still be sized properly. Lastly, we have our single wing rotor for handling, I call these, the very high particulate density fluids. If there's a lot of particles in your fluid that are fairly large, you are concerned with cutting them or damaging the product quality, what we do is we'll take one large unbalanced rotor and put that in the pump as opposed to the traditional bi-wing rotor. This just allows us to handle those large particulate densities where large particulate integrity is essential. However, that now becomes an unbalanced rotor, so we can't run these pumps anything above 300 RPM. So a note of caution there. As we start looking at the mechanical and O-ring seals that we have within our pump portfolio, I wanted to just cover again the families like we did with the pumps going in. Universal 1 is available in single and double O-ring, as well as single and double mechanical. There are some other O-ring options, such as U-cups and quad rings. However, those are very uncommon in the Universal 1. In the Universal 2, those are available in single and double mechanical, as well as that single and triple lip seal. And then there are some special options that we'll cover in just a few slides. The Universal 3 has both O-ring and mechanical seals available. And then the Waukesha twin screw is a single or double mechanical cartridge seal for fast replacement to maximize your uptime there. With the O-ring seals, it's a very simple design. We'll use one of those sleeve materials, either zirconia or 316 stainless, and slide that over the pump shaft to give that O-ring a surface to make contact with that's not going to wear our shafts down. They're simple to install, very easy to clean, and definitely our lowest cost seal offering that we have. So we see these very commonly in the U1 because the U1 is clean out of place only. It may be tore down once a day, once a week. So it's very easy to do those seal replacements when you're cleaning out of place. The big disadvantage that I see is the pressure and temperature limitations, 100 PSI and 180 degrees Fahrenheit there. As we look at the single mechanical seals, we'll cover those seal seats a little bit later in the presentation. But the big thing with mechanical seals is they have a much lower maintenance requirement than O-ring seals. They can last for extremely long times and are very common in the Universal 2 and Universal 3 because those pumps aren't getting taken apart very frequently because they're cleaned in place. The other nice benefit there is they're good for the entire temperature and pressure range of the seal faces and the pump families. So you get very long life out of these pumps. The big drawback here is these seals are a little bit more fragile than an O-ring. So it's important that we take great care in installing these to make sure we're not getting any chips, nicks, or dirt buildup on these as well. The double mechanical seal is essentially, you have a single mechanical seal that's making contact with the product. And then we put another set of seals behind that first set of seals to create a liquid chamber that we can actually flush that pump so that you can either cool the seal faces, flush away any particulate buildup, make sure that we're not getting anything that could damage those seals. A very common question that I get on these is, when should I use a double mechanical seal? The first thing that always drives me towards a double mechanical seal is going to be if it's a sticky or sugary product, it's got some abrasiveness to it, or it's got any sort of hazardous or corrosive qualities to it that could damage the seal. So with that double mechanical seal, what we see is as we introduce that flush fluid, we're cleaning away that sugary product or that abrasive product and not allowing it to make extended contact with the seal face and not build up any product or cause premature wear within that double mechanical seal. Some other applications where I see double mechanical seals used, high temperatures for extended periods of time. If we're using a 300-degree product that's being pumped with one of our pumps, you may see some premature seal failure because those seals get so hot and wear much quicker. By using a double mechanical seal and providing some cool flushing fluid into that liquid chamber that we discussed, you can extend the life of those seals greatly. The other concern that would push us into a double mechanical seal is if that pump has a chance of running dry. These seals will wear and get damaged within seconds of running dry. It may not seem like you only ran that pump for a few seconds. That could be enough to cause that damage to those seal faces. So by providing that flush fluid, the seal always has some sort of fluid to keep it lubricated. And that's what I tell people with either single or double mechanical seals. Our seals need a fluid on them to ensure that they're lubricated and running properly. So that either means for a single mechanical, a flooded suction, or for a double mechanical, make sure that flush fluid is started before you turn the pump on if it has a chance of running dry. We also have a lip seal offering for our U2 and U2ND pumps now as well. This lip seal is brand new. It just got released this quarter, and I'm very excited to kind of see where our industry takes it with our Universal Series pumps. It has an extremely long life due to a proprietary modified PTFE, which also gives us a very robust design with a lot of chemical resistance. The big thing here is there's only one wetted O-ring and no moving O-ring. So we're reducing the risk of having that O-ring hang up or clog, while also reducing the amount of product contact coming in for those very corrosive industrial applications. It's also very easy to maintain. It has a self-aligning design, so you simply pop the lip seal out and put a new lip seal in, and you can't really put these in incorrectly. We'll see these a lot as a lower cost option in the general industrial space or some lower cost sanitary applications that don't require CIP. So I'm really excited to see where the market takes this one and see what we can really do and push the boundaries with. Some more specialty seal options, the first one being our narrow face seal within the Universal 2 pump family. It has the same design as a single mechanical seal, except we've reduced the size of the seal face. You can see in the picture there, we've cut that seal face size in half. So if you think about pressure as a force over an area, we've cut that area in half, which means we've doubled the amount of force that seal is exerting on the opposing face. So what we've also heard this called is a knife edge seal because it's going to cut away product from building up on the seal faces. We've seen these used a lot in like the confectionery and candy industry, where they're not providing any flush fluid to the pump, but that narrow face or knife edge seal is cutting away that abrasive or sugary product from building up on the seal. So they're getting very great pump life without actually using any flush fluid like a traditional double mechanical. We also have the high pressure barrier seal. So the way I explain high pressure barrier seals is pretty simple. When a traditional seal fails, the product is going to leak from the product zone out into the atmosphere. With the high pressure barrier seal, it's the exact opposite. We're going to pressurize that seal chamber so that if there is any seal failure, the flush fluid is going to leak into the product zone rather than the product leaking out to atmosphere. So we see these a lot in industrial applications where you have like a pressurized seal pot, or in sanitary applications where they're pumping something maybe alcoholic and they don't want to put anything flammable into the atmosphere. You can see the calculation there on the bottom of this seal, but essentially we're just pressurizing that seal chamber to ensure we get the failure mode that we're looking for. When it comes to mechanical seal faces, we have a lot of different options. Starting on the left here with the carbon, this is the lowest cost seal face in our portfolio. It's a little bit softer of a seal face and has some self-lubricating properties. So it's great to pair with a hard seal face like silicon carbide or tungsten carbide because that hard seal face and softer seal face mesh together really, really nicely. However, carbon really doesn't handle abrasive applications because it's so much softer. Ceramic and chrome oxide seals are a more robust seal offering. They're harder than carbon, not as hard as silicon carbide, but they are significantly tougher, such that if you're taking that pump apart daily, the ceramic or chrome oxide seal faces are going to be a great option for you because they're going to be a little bit easier and a little bit safer to put on that seal without chipping or breaking the seal. Silicon carbide is our hardest seal face that we offer. However, it is very brittle. If you're putting that seal into a pump and accidentally clip it on the shaft as you're putting the pump body back in, that may be enough to cause a little bit of damage to that pump seal and cause some seal failure right away on startup. However, it's still a really great seal option for abrasive applications or meshing with carbon in most standard applications. Lastly, we have tungsten carbide. That's going to be not quite as hard as silicon carbide, but a little bit harder than our ceramic and chrome oxide options, and it's incredibly tough. I have dropped it on the ground onto concrete, picked it up, reinstalled it into the seal face, and put it together. Pump ran great. So this is great for anything that's got any sort of crystallization, anything that is very corrosive. Tungsten carbide is going to be the most expensive option, but will work in almost any application. Now, let's get into sizing these pumps actually. We've talked about how to configure them properly. Let's talk about sizing and selecting the right pump now. First, it's important to understand how universal series pumps work. Our universal series pumps are ECP style positive displacement pumps or external circumferential piston pumps. Essentially, this pump operates by opening that inlet, which you can see on the left side of the picture here, and allowing that fluid to flow into the inlet side of the pump. That's why that inlet pressure available is so important. Then we're going to carry that volume through the pump. Pardon me. We're going to carry that volume through the pump around the outside edges of the pump. That's what we call our carry-through volume. This does not pump through the center line of the pump. It pumps around the outside edges. As we get towards the discharge side, that cavity collapses and we push that fluid forward. So every time that pump rotates, we're getting 1 unit of volume moving forward depending on the size of the pump. What that means is flow can really only be adjusted by adjusting the speed. If you're not running this pump on a VFD, that means if you need more capacity out of that pump or more speed, you're going to have to switch out that gear reducer to let that pump run at a higher speed. If you are running them on a VFD, you can just adjust that frequency. But again, make sure you have enough horsepower available there. This is also very important to understand because if the pump is deadheaded, it's still going to produce 1 unit of volume for every revolution, which creates extremely high pressures almost instantaneously. That's why we always recommend using a relief valve in the piping system. For example, you can see the picture below. You would set that to a certain pressure level, maybe 200 psi or 300 psi. And whenever that pressure is reached, it pops the valve open and allows that fluid to recirculate rather than truly deadheading and causing significant damage to your pump. There are 2 main approaches to sizing positive displacement pumps, and that's going to be the paper curve on the left, or as you see on the right, a much more simplified version of the pump curve with some backup sizing data that is done using our online sizing program. Let's start with the paper curve. The biggest example I like to give here is first, this is done using water. So these lines all show water being pumped. If you're pumping something, again, above that 200 centipoise, if you're pumping something, say 1,000 centipoise, you would size that on the 0 psi line. Water being pumped against 0 discharge pressure is going to be 100% efficient. However, if you're pumping something lower viscosity, like the example I've given on the screen here, pumping a 10 centipoise product at 100 psi pumps like water at 25 psi. And you'll see my drawing is a touch off here, but if you take that 10 centipoise line down to 100 psi, you'll see that that roughly aligns with the 25 psi line. So how you use this slip correction curve, we'll use the line that's drawn here. If I have a 3 centipoise product at 100 psi, I would draw that line from 3 centipoise down to 100 psi, and then draw a matching parallel line back down the pump curve to get the actual slip corrected flow line. So you can see that that's just a touch more than 50 psi, somewhere between that 50 and 100 psi range. So those are the curves that you would use then to size your pump. The next thing we would calculate is the horsepower required. This is a combination of 2 things, the water horsepower and the viscous horsepower. The water horsepower is simply a function of the discharge pressure required and the speed at which you're running that pump and the flow rate. And the viscous horsepower is determined by testing. We sum those 2 things together to get what you see on our quotes, which is the BHP or brake horsepower. In practice, I've taken a separate line here. This is not connected to our previous sizing on the slip correction factor. But if I have a 5,000 centipoise product being pumped at 100 psi, it requires just over 3 horsepower. So you see in that green line going straight down the center, 100 psi for the water horsepower is just over 1 horsepower. And then we go down and do our viscous horsepower calculation, and that 5,000 centipoise product is just over 2 horsepower. So we'd probably put a 5 horsepower gear motor on this application. Now, when we look at actually sizing our pumps, this is where the electronic sizing program really starts to shine. If you take Process 1 and process 2 here with water and high fructose corn syrup. On the paper curve, you can see them drawn by the blue and red lines. And you can approximate if you look at the curve and see that it's about 250-ish RPMs for the water, and it's about 125-ish RPMs for the high fructose corn syrup. You can get approximate horsepower calculations from that as well. However, if you look at what we've done with the electronic sizing program, you can see in the size model 60, running at 257 RPMs and 131 RPMs for this calculation. You also get the exact horsepowers of 1.1 and 1.2, as well as the efficiency and slip associated with those processes as well. So what I like to tell people is paper curves can get you pretty close. They can get you the right pump model for your application. You can see that, yes, a size 60 works really well. However, it's difficult to get precise data off of a paper curve. Thickness of the lead of your pencil as you draw your line may alter the actual speed. How straight you draw that line with a ruler. Is it perfectly straight? Maybe, maybe not. So I recommend that people use the paper curves to get the right pump size, and then reach out to our applications team or one of your channel partners, and they can do that online sizing for you to get the exact parameters. When we look at what those exact parameters need to be to get the sizing done, we need to have 4 main things: the flow rate, the differential pressure, the viscosity, as well as the product temperature. As we discussed before, product temperature is critical for rotor selection, and the viscosity, pressure, and flow rate help us get the rest of the way there. Some nice things to have are product characteristics, if you have them. Are there solids? Is it sticky? Is there abrasiveness to the product? Do you have any special motor requirements like explosion proof or stainless steel, as well as the port connection requirements that you may require for your pump as well? Now, jumping into some specific application examples, first of all, we're all over the place. We're in food and beverage, we're in dairy, we're in pharmaceuticals, we're in the chemical and industrial space, and many other spaces as well. So if you have an application and you're not quite sure how to tackle it, chances are we've probably already done it, and we can get you pretty close, at least pointed in the right direction to get the right pump for your application. Let's look at a specific example and talk about how some minor details can really affect the sizing of that pump. Example number 1 is a nut butter, maybe peanut butter, almond butter, something of that nature. And for all of these examples, we're pumping them at 55 gallons a minute with 100 psi of discharge pressure and a product viscosity of 15,000 centipoise. Now, I've rounded the numbers on this sizing just to keep things simple, but here's the sizing parameters we get for we're told it's a nut butter of some sort. We'd size a U2060 at 400 RPM, 10 psi of net inlet pressure required, and a brake horsepower of 10. So for the speed of that pump, you'll notice 400 is what I've selected, and that's generally what we're going to aim for at the high point for continuous operation. When we're sizing a pump for continuous operation, we like to run it around 2/3 of the maximum pump speed available. So with the U2060, it can run up to 600 RPMs. Therefore, I'm going to target 400 for my actual sizing, just to make sure that we're not overworking that pump. You don't drive your car at 6,000 RPMs all day. You drive it at 6,000 for a bit, and then you may cruise at 2,000 RPMs. The same principle applies here. Now, if we change that example to a crunchy nut butter with added sugar, would we use the same pump? Would we use the same speed? Would we still use that single mechanical seal? And the answer is we'd actually size that pump up in size. We'd go from a U2060 to a U2130. We would run that pump slower than 400 RPMs. Because we've sized it up, it's going to have a lower net inlet pressure requirement. And the seals, we are going to select a double mechanical seal. You could also use a single mechanical with narrow face seals like we had discussed in the seal section prior. Now, the obvious question is, why did you size the pump up? And here's your answer, everybody. We really want to limit pump wear. That's the number one thing. So by increasing the pump size, we can displace more units, more volume per revolution, and therefore we can run that pump slower. every revolution of that pump is going to cause some form of damage. It's going to cause some form of wear because it's abrasive. There's sugar, there may be some peanut butter dust or something like that that is abrasive as well. We really want to limit the pump speed as much as we can. Or, for example, with this cured meat example on the right, salt. Salt is very abrasive. So if we can run it a little bit slower, we can lower the rate of pump wear. Depending on the application, we may increase the rotor clearances. If our rotor clearance is 0.002 or 2 thousandths of an inch to 4 thousandths of an inch, and the particles are 4 thousandths of an inch, it's going to wear open those clearances much more quickly. So we may select a larger clearance rotor like the extra hot clearance rotor to allow those particles to freely slip behind the pump without causing additional wear. For seals in abrasive applications, we almost always want to select a double mechanical seal with those hard seal faces, either silicon carbide or tungsten carbide. And again, we could consider narrow face seals if double mechanical seals are not an option. And lastly, for abrasive applications, we do have tons of different special coatings, such as a thin dense chrome, a diamond coat, a sanitary diamond coat, as well as a surface hardening treatment. Now, I don't expect you to be experts on these. All this to say, there are options for your abrasive applications should you run into one. Moving on to a third example here, we're back to just our standard nut butter. However, this time we've added 3/4 inch hole nuts. And you'll see that I've added the pump inlet size on the previous two examples for this consideration. Using the two previous pumps, how would you configure this pump? And when we look at what the actual outcome would be, we would use a U2 130 with a 3-inch inlet. And we'll get to that in just a moment. Again, because we've sized that pump up, we're going to have a slower pump speed, a lower inlet pressure requirement, and a lower horsepower requirement. Because there's no added sugars, we've switched that back to a single mechanical seal as well. So when it comes to handling particulates, the first and most important thing is that particle size should be 1/3 or less the size of the pump connection or the pump inlet. Essentially, we're just concerned with clogging or deadheading or clogging the suction side of the pump that would cause that pump to run dry and cause damage. So with a 3-inch inlet, 3/4 inch is less than 1/3 of that size, so we're good. However, with a 2-inch inlet, the inlet's just too small to handle those particulates, and we would avoid using that. We also like to avoid the small model positive displacement pumps, that being the size 0.6, 15, and 18 size pumps. And that's just essentially the pump body itself is very thin. There's not a lot of depth to it, so it can cause some unnecessary shear to our particulates. We also like to run these pumps slower. As you saw, we sized the pump up. That wasn't just because of the inlet size, although that was guiding it. We also do want to run that pump slower. The slower the pump speed, the less quote unquote clips of the product. And what we mean by that is as the pump body rotates, as you can see kind of the open pump body on the screen, every time that rotor is going to cross over the inlet and could cause some sort of damage to your particles. So it's important that we run these slower and cause less chance of damaging the particulate integrity of your product. We also like to operate against lower pressures. Higher pressures generally just put a higher stress on the particulates and can cause not total damage of the product, but degradation of quality. And then lastly, we covered one of those special rotors with the single wing rotor. There are less clips of the product because instead of clipping twice every rotation, now we're only clipping once every rotation. So for very high particulate densities, this can be a great option to maintain high quality particulates through the entire processing system. And very lastly, on the note here on the left, universal pumps are indeed considered high shear products. They are a high shear device because anything that slips through those crevices that are 0.002, 2 thousandths, or 4 thousandths, or 6 thousandths of an inch are going to get sheared immensely. That is a high shear zone. However, as I stated at the beginning, anything over that 200 or 300 centipoise is going to be 100% efficient, meaning absolutely no shear. Well, some shear, but a very minimal amount of shear compared to those tight clearances. So high shear is really only found in those small clearances. And if you're 98% efficient, only 2% of your product is experiencing that high shear. Everything else is very gently handled. So although it's a high shear device, I would ask you, how much of your product is being sheared and how much is that affecting product quality? The last kind of application example I wanted to cover with you all today is chocolate applications because they're a two-phase media. And chocolate applications can be very difficult to process. You have two things going on with chocolate or any two-phase media. You have something that's pump friendly, in this case cocoa butter, and something that's not pump friendly, such as cocoa powder, milk powder, sugar crystals, and things like that. What we find with these two-phase media is that they are very likely to separate. And what happens as they separate is the fluid that's easy to pump is pushed along quite nicely. The fluid that is not pump friendly, or the powders in this case, will separate out and build up in our pump cover area. As you can see, we call that hockey pucking. And in the image, you see an example of those hockey pucks. Those are chocolate particles that were left behind as the butter was pumped, and they build up and cause immense amount of friction and can actually completely lock up and destroy your pump. So we have to handle these very, very carefully. For two-phase media, the first thing we're going to recommend is extra hot clearance rotors. And I say recommended loosely, it's almost a requirement here. The added clearances will promote some internal circulation. They will slip a little bit more, but in this case, the slip is actually very helpful because it continues to mix those powders that may separate back into the homogeneous stream of fluid. We also like to run these at very slow RPMs to prevent that separation of fluid. The powder, the cocoa powder, the milk crystals, and the cocoa butter all have very different densities. So if you're spinning them super fast around the outside of that pump body, you're going to cause them to separate just from inertia. So by running that pump slower, it lowers the rate of phase separation and keeps that product much more homogeneous. The other last option that we have, if you're using our Universal 1, is we can introduce what we call our CIP flats. Essentially, we mill two small flats onto the rotor. That big round block in the back will mill a couple flats in there to introduce a new slip pathway. As we saw in the previous slide, behind the rotors, or what's facing out towards us from the screen, that's where the product's going to build up. So if we introduce a slip pathway, we can slip product back through and prevent that hockey pucking from happening. For Universal 1s and Universal 3s in chocolate, we've best found the O-ring seals to work. We'll use a double O-ring seal, and instead of using a flush port, we'll use a grease zerk, and we'll use compatible food grade grease or cocoa butter as the flushing fluid, just to ensure that we're not adding any water to the chocolate process. You can also use a narrow face seal here. We've seen those kind of rising a bit to ensure that you're cutting away those powders from building up on the pump itself. So this ends today's presentation, and I will now begin our question and answer session. Just a quick note for y'all. After we complete this webinar, all participants will receive a copy of the presentation. And, I say this at the end of every presentation. I really do encourage you to let us and let myself know, how was today's presentation? Did it provide any useful information to you? Is there something you wish we would have covered more? We're always looking to understand the value of our content and improve the content that we're providing to you all. Now, please just give me a quick moment while I pull up your questions. Thank you guys for listening into the presentation. We've got a couple questions here coming through. First one being, what makes the ECP rotor design better than a traditional lobe style pump? And that really comes down to three kind of key features. With the ECP style pump, you have a nice rounded long slip pathway. So that's going to give us a little bit more efficiency in the sense that there's a longer pathway for that product to slip through before it passes back to the inlet side of the pump. As that pump continues to wear, with lobe pumps, you just have a rounded kind of singular point, so to speak, of failure. Once that singular point starts to wear, you get exponential decay of the clearances and exponential decay of the efficiencies as well. And the third thing, if you're handling any particulate applications, uh, the Universal Series ECP style pump has that shovel nose design. So when you go to restart the pump, it's going to gently scoop that product and recreate a homogeneous stream. With the lobe style pump, because it's rounded at that point, those particulates can build up and create a pinch point that can actually lock up your pump or potentially even throw it out of timing in that rotor hub area where the ECP style pump requires no timing and can very gently rotate around on the side of the pump. Let's see, what else do we have here? The next question here. Can I use a U2 or a U3 pump for both product and CIP, similar to a twin screw? For applications like that, yes, but is always the answer that I give people. With a twin screw, the big advantage of being able to do product and CIP at the same time, you have a wide speed range. You can run that pump a few hundred RPM. You can run that pump all the way up to 3,000 RPM, sometimes even higher than that. So you get a wide range of speeds that you can actually pump at. With the Universal Series, you just have a smaller range of speeds, which makes it a little bit more difficult to fit both product and CIP into those applications because we have 600 RPM range rather than 3,000 RPMs of range. So just something to keep in mind there. Let's see, what else do we have here? Next question here, do you change anything on your seals and rotors between different liquid egg products, such as egg whites, egg yolks, salted yolk, and whole egg? The big thing there is going to be on the viscosity and the abrasiveness of the product. So something like a salted yolk, that salt is a very abrasive product like we touched on. Sorry, making a quick change here. That salted egg yolk is going to be abrasive, so we may recommend doing something in the seal configuration like a double mechanical just to keep washing that salt away to stop it from building up and wearing those seals down. And then with things like egg whites, they're a little bit easier to pump, so it's not something that we're as concerned with in the seal area. And on the rotors, generally it's just going to be driven by the efficiency, making sure that we're running as efficiently as possible and we're not limited by temperature, which in eggs we're generally not. But great question, thank you. Let's see, what else do we have here? Try and get one or two more in before the end of our call. I got a bunch of questions coming here. So there's a question that just came in. In our 3 cases of the selection with nut butter, you increased the pump size from a U size 060 to a size 130. And the question is, why would we do such a thing? And back when I was covering the abrasive parts of the presentation, the big thing that we're concerned with there is pump wear. So by sizing up that pump, what that allows us to do is displace more unit of volume per revolution. So every time that pump rotates, because it's a larger pump, we're going to displace more fluid. So if you have a certain flow rate requirement, that means we can run that pump slower. And every rotation of the pump with an abrasive application, you're getting some amount of wear. So if we run a smaller pump faster, it's going to be rotating quicker, it's going to be wearing quicker. So by sizing up that pump to a 130, we can run it slower at slower speeds, which is going to give us less wear over time, or reduce the rate of wear, I should say. But great question there as well. What else do we have here? Gosh, a lot of questions, guys. Thank you so much. While I'm looking through them, I will say, I know I'm not going to be able to get to them all today, so I will be sending out kind of an FAQ to all of you who have come, kind of just answering all the questions that you have along the way, along with the presentation as well. That will be coming from the SPX Flow team for you all. So another question that I have here is on the front-loaded seal design. How much maintenance time is saved with the front-loaded seal versus the Universal 2, which is in the back of the pump body? That's a great question. Um, and where I think the U3 really shines in applications is once you start getting into two different scenarios. The first scenario, once those pump bodies start getting larger, in the size 130, size 60 and larger, you're getting bodies that either require two maintenance technicians to remove the body because they start getting so heavy, or as you get even larger than that, you require some sort of lifting mechanism, whether that's a crane or something like that, to get the body off just to replace the seals. That can take a lot of time just to get that body removed. While the seal replacement itself is pretty easy, just that added time and added manpower can be difficult and add some time. With the Universal 3 being front loaded, you never have to remove that body on those larger pumps to actually replace the seals, which I think is a really huge benefit for everyone. And then the other piece is in those hard to reach areas. If you're under a tank with piping all around, it can be quite a hassle to just remove that body. You may be crawling on your hands and knees or laying on your side trying to slide that body off. With the Universal 3, you just don't have that hassle. So the maintenance time saved is not necessarily in the seal replacement itself, but just the fact that we don't have to remove that body, whether it's heavy or hard to remove, can save a lot of different time. Looks like I have time for about one more question here, and a good one just came in. What would be the best option of the Universal series for ice cream production? So ice cream production, first of all, it's an abrasive application, so we would like to run it slow or slower, I would say, because of all the sugars and abrasiveness. And then it really depends on, are you cleaning that system in place or is that pump being taken apart daily? That's the big thing that drives me between the different pump families. If you're taking it apart daily or cleaning it daily, the Universal one is the easiest pump to work on. So I always select that when pumps are getting torn apart and rebuilt frequently or just cleaned out of place. Once you start doing any clean in place, I think the best option becomes the Universal 2 or 3. And like we just touched on with the maintenance time, the difference between the U2 and U3, they're both able to be cleaned in place, but it's really a kind of a preference on how you want to replace those seals. So that's bringing us right about to the end here, and I want to keep us right on an hour to be respectful of everyone's time. Again, I'll be able to follow up with some of the FAQs for the questions I was not able to get to today. But truly, I want to thank you all for joining. We had a great turnout. I'm really glad just to share this information with you all. I hope it was insightful. I hope you learned a thing or two along the way. And we want to thank you all for joining the webinar. And with that, we'll end the call. And thank you all very much for joining.